class 9 students, very warm welcome to Deeksha Vedantu. I'm your Aditi Ma'am, and today is the most awaited chapter, and I'm finally here with that journey inside the atom. We are going to dive into it, explore what is exactly inside the atom, and we will see all the important points that you need in your class 9th. Plus, I will make it so interesting and just like a story. See, this chapter is full of all the stories, a bit of history, a bit of scientists, what they actually did. So it's kind of like a story, just flow with it. And I still don't understand why students get so feared of this, because this chapter is so lovely and I will show you that today. Okay, so let's start this chapter without any delay. Before that, subscribe the channel and like this session, because we are coming live every day, so you can join the live sessions, ask your doubts, get questions cleared, do all the previous year questions and all those questions. Plus, we are giving you one shots of all the chapters that you need in your class 9th as well as your class 10th. So hit the subscribe button. Okay, now beta, journey inside the atom. Now atom, see, it started with just a very simple question, just like Newton asked why this apple fell down, right? Exactly the same way, more other scientists, more people in our history asked, what is exactly everything is made up of? What is I am made up of? What are you made up of? What is this pen made up of? What is this color made up of? What is this slide made up of? What is your pen, your copy, your mouth, your ears, your eyes are made up of? Your lenses are made up of? What is exactly there are in these things? That is, what is that? Okay, so beta, that is eventually we know now by atom, but let's go through their journey of how they invoked their idea of atom, right? Now beta, first let's study the history, and it's very important that you study the world history, but it's equally important that you study your own history as well, that you are descendants of some of the great philosophers in the world, and you should be proud of that. Okay, and you should know who those philosophers are. So NCERT took a great step defining this. So this is an atomic story in ancient India, what exactly happened. So there was this very great philosopher Acharya Kanada. His name was Kanada, okay, and he asked a very simple question: what is everything made up of? And in his whole theory, in his whole findings, he found out that the smallest unit, which we actually call atom, is actually, they name it as Parmanu. Right? We hear now Parmanu bombs. What are those? Atomic bombs. Okay, atom bombs. So what is that? That is Parmanu, originated in India, okay, by Acharya Kanada. Now he wrote all of that in Visheshik Sutra. Right? So what they said, that this Parmanu, it's a very indivisible particle. That means it cannot be further broken down. Okay? It was then times theory, right? And it is infinitesimally small, cannot be perceived by the senses. You can see me, but you cannot see the individual atoms I am made up of, right? You cannot see those atoms. We are not, our eyes are not equipped enough to see those small atoms, right? But these are existing in the nature from the starting of even time. Right? We all know that. And that we called in our Indian language, Indian science language, that is Parmanu. And on that, we said that this is dyad, we call it, but this is triad, tetrad, and so on. So this is made up of 2 atoms, okay? This is made up of 3 atoms, 4 atoms, and so on, right? So in Hindi or in Sanskrit, we call it Devya, Chetra, something like this, okay? So this is originated from way back in India, and that is the story. So everything that exists, from a pot to a tree to a cow, everything is made up of atoms, including you and me, including all the non-living things. Now same story was happening in Greece as well. Greek philosophers, we are hearing about a lot of Greek philosophers, right? Because Greece was as ahead of the time as we Indians were in that era. right? So the atomic story in ancient Greece was what? We had two very great philosophers, that is called Leucippus, okay, and Demetrius. Now these people, they again asked the same question, that what is everything made up of? What exactly is the smallest unit that makes everything up in this whole world? And they call it atomos. That is the Greek word for atom, right? So there we got its name, and they broken down pieces, this big piece, into smaller to smaller into smaller, and finally into the one undividable particle, that is our atom. Right? Now this was basically the idea of atom again. Different combinations and rearrangement of atoms give rise to all kind of objects and substances, and we know that, right? Different arrangement of atoms make up this book, but atoms are same, but I am a different person. This pen is a different person, right? So all these things comprise of atoms, but their rearrangement, because of their rearrangement, all these things are different, right? So this is the basic story of your where the atom actually originated from. So the idea of atom came back 2000 years old, born in ancient India and Greece. Okay, Acharya Kanada in India, dividing matter, that is dravya, we call it, right? Again and again reaches the smallest indivisible particle, that is Parmanu, recorded in the Vaisheshika Sutra. Right? Now this is the story of India. When these Parmanus combine, they became dyads, triads, whatever you want to call it, their pronunciation, correct me if I'm wrong in the comment section. And so this was the Indian story. Then we had the Greek story, Leucippus and Demetrius. We have in Greece, they are indivisible particles called atomos, that is Greek for indivisible. Okay, these were imaginary or philosophical ideas, not based on experiment. Okay, these were just the philosophers talking. Okay, so there now we know in new NCERT we have a think like a scientist column, so we have incorporated that in this sessions as well. In an atom, truly the smallest indivisible unit of matter, or can it be divided even further? Now we all know, we all studied cell, right? We all studied cell, and we know that is also a fundamental structure, but inside cell we have so many things, right? And then we studied them individually as well. Similarly, a lot similar, that is our atom. Now we'll slowly build up, I won't tell you everything, but we'll see what atom consists of, what is there inside the atom, how they are reacting, how they are like flowing inside the atom. We'll see everything. Okay, so basically two lands, one question. Greece, India, they only had one question, what is everything made up of? In India we called it as Parmanu, in Greece they call it as atomos. Same insight, centuries apart. Okay, now beta, let's dive a bit deeper into the scientific part of it. Okay, because we are studying science and we are scientists, at some level we are. Okay, now beta, first after this, after the idea of something indivisible, after the idea of something very fundamental, very small, new scientists came up. So people who were this idea of atom was philosophical actually, but now it is translating into scientific manner, into more scientific manner, right? So in 1808, that is 1808, Dalton's atomic theory came. So Dalton, of course, was a scientist. He was the first one who experimentally based, whose description of matter was a little bit of experimental based. Okay, he said that all matter is made up of tiny indivisible particles called atoms, the fundamental building block that cannot be broken down. So his words were, here remember, these are some things you will have to remember. Okay, so his words were this, that cannot be broken down. That is what Dalton said. Okay, now it became the starting point for our modern understanding of atomic structure. See beta, you might ask this question, ma'am, let's just see the final structure of atom. Why are we studying all the structures which are failed, right? Because beta, when someone is the first one to give a theory that atom can't be broken down, then only we started to study atom. right? So we should know the origin point, and for me, you should have massive respect for Dalton. He was the first one who had enough guts in him to say that this is the stuff that makes up the whole entire world, that makes up the entire entity of this world. That takes massive confidence, right? And to trust yourself in yourself that okay, atom is the first thing, that atom is the smallest thing that makes up everything, and it cannot be divided. And he knew, every scientist know that they are going to be proved at some time of the point as the new discoveries will come, especially the ones who give new discoveries. Okay, so Dalton has my massive respect. Now it's on you. Okay, so we have to give them a respect that what they came through. And also in this book we are studying about how scientists think, right? So you cannot know how someone thinks if you cannot see the most basic, their most basic ideas, their wrong ideas, their improved ideas, their thinking, how they thought. So we are thinking about how they actually went from a single ball of atom that was not broken down to an atom that is to string theory now, that is like the most deepest part of the atom. And this whole evolution is worth studying because at some point we are going to do the discoveries. Okay. Now beta, this Dalton said all this. Now this theory raised of course so many questions. Okay, what are atoms made up of? I call it, this is the smallest unit, but I can still ask, what is this made up of? Okay, then would they look like, what would they look like if we see them? Okay, what makes atoms of the element differ from another? Why this yellow color looks like this but this blue color looks like this when they are made up of simply atoms? Then why are they different? Why am I this specs different? That's the one question that raised after Dalton's atomic theory. Okay. Next beta, that is the basics of something that we understand the inside of atom. Now after that, what was happening in J.J. Thomson? Okay, J.J. Thomson was a scientist and you will learn about him a lot more. He was not studying about atoms, okay, in the first place. He was actually just doing some experiments with gas. Okay, he took a gas inside this tube in this chamber and he was passing the current. Okay, simple electricity inside the current, but he saw something, he did something, right? He put two cathodes, one cathode and one anode inside that gas chamber to flow the current, right? And now these are connected with the outside battery from where we let the current flow, right? Now I've told you that anode is always positive, cathode is negative. How to remember that? A, B, C. Anode comes first, so it gets the positive charge. Okay, done. Okay, so anode is positive, cathode is negative, and he saw something that whenever a voltage is applied between these two, whenever a current is passed, let's say for now, so what happens? Some rays are emitting out, this cathode is emitting out some rays and they are then traveling towards anode. They are exiting out from cathode and traveling inside towards the anode, right? So he named them as cathode rays, okay, on the basis of they were emitting out from cathode. Right, so late 1800s, now that was 1808. After that, late 1800s, some elements emit radiation, prove that atoms are not indivisible. See, there are so many things, so many elements that emit radiation. Now we know it's uranium, but until then, J.J. Thomson didn't know that uranium is radioactive. Right, so but they saw that there are some elements, they are decaying. Okay, over the period of time they are decaying, so something is coming out of them, right? And they produced a result that atom is not indivisible. It can be further divided, but they just didn't know how to prove it, right? So he was randomly running this experiment and he saw this and he passed the current through gas, okay, at very low pressure. This is the main point of this, very low pressure, and called them cathode rays, from cathode to anode. And then he changed the environment. He did it with electric fields, he did it with magnetic fields, and he found the same result. okay, and he found that the elements of this cathode rays, they have mass lesser than atom. They have mass lesser than atom, and if something has mass lesser than atom, then atom is not the smallest unit. It is not the smallest particle. It is not indivisible, right? So he said that in electric or magnetic field, these are negatively charged particles. They have a charge. They have a mass lesser than atom. But atom, we'll study. 2 minutes. Okay, they were negatively charged particle and had mass lesser than atom, and hence he called it as electron. Okay, he named it as electron. Done? Now beta, he also saw that these rays are independent of the nature of gas that was inside this chamber, the nature of cathode or anode rays, and these electrons are present in every atom. He finally gave the theory, okay, because atom is indivisible. That is somehow true on this level, but inside that atom you have electrons that are running from cathode to anode. Done? Then beta, he simply named them electrons, and he saw that the charge of electron is 1.602 10 raised to power minus 19 coulomb, and it is taken negative just for the convenience, okay, because they are negatively charged, we know that. Right? Now beta, atoms have no color, okay, colors in all these diagrams are only for illustration, so make sure that you don't think that these atoms are colorful, okay. Now although there is something you will learn, not color theory, there is something you will learn that the color inside everything is due to the atoms, due to the radiation of atoms. So make sure you watch this video till the end. This is a random information, but I'll give you, it's very interesting. Okay, now beta, let's go to the next slide and actually see what happened after we discovered electron. Now J.J. Thomson, okay, he discovered electron during this gas chamber experiment where he saw that a negative charge is running from cathode towards the anode, that is negative to positive, and since it is going towards the positive road, it must be negative because positive and negative attract, negative negative, positive positive repel, right? Now but there was one question that was asked by everyone that was there, that if atom is made up of electrons are negatively charged, then atom should be negatively charged. But atom is neutral. We know that. I don't have current. I am not negatively charged. So atom in itself in general is neutral, right? Then how this electrons that are negatively charged, what are these getting balanced by, right? So then Thomson said, he said, okay, listen to me, that I propose that atom is a sphere of positive charge. It is a mass of positive charge, and inside that electrons are embedded in it, okay, just like a watermelon. Okay, so he said that it's like a watermelon. The atom is like a watermelon where the red pulp is the positive charge, the seeds are the electrons. So this was basically a first genuine attempt to say that atom is neutral and it has equal number of positive and equal number of negative charges, and these are balanced, and they have to be balanced because atom is neutral, right? Okay, but he gave the theory. Okay, everyone was a little bit happy until sometime, and that sometime was what? Now after this everyone was happy and all, but Rutherford, Ernest Rutherford, okay, and under him there were his two scholars, Geiger and Marston, okay. So these two were performing an experiment where they had a gold foil. Now we know aluminium foils. Now instead of that aluminium foil we have gold foil, okay, sheet of gold. Now they were firing alpha particles. What are alpha particles? They are positively charged particles. They are positively charged particles are our alpha particles. This is the symbol for alpha particle. Okay, now when they did this experiment, they saw a very good thing. Let me draw it out for you. Let's say this is your gold film, okay, and they fired alpha particles from here, okay, and they saw that when this alpha particle is going, so they went right through it. They went right through it. They sent so many alpha particles, and they said that these alpha particles all went straight. Okay, all went straight. Now see, very important, they say that they expected that all pass straight or deflect slightly. Now according to Thomson, right, the atom was simply a positive charge and some electrons are there. Now if you charge alpha particles on this gold foil. Okay, remember this gold foil, let's not just take a huge gold foil, let's just take this as one atom. Okay, let's just take this as one big atom, okay, for now. And an alpha particle is going, okay, this alpha particle is going towards them. Okay, now they fired this alpha particle again and again. They fired one alpha particle and it went straight through the atom. They were like, okay, and they fired again another alpha particle, it went straight. Then they fired one alpha particle and it got deflected a little bit. Then they fired again one more alpha particle, it got deflected a little bit more. Okay, then they fired one more alpha particle right at the center of the atom and it got deflected almost 180 degree. Do you see this red one? This is the reflected particle. So what is happening? They are firing an alpha particle, mostly it's going straight, it's passing through the atom, or it's getting a little bit deflected. But what happened? When I fired the alpha particle right at the center of the atom, it almost deflected back on the same path. That means what? That means that alpha particle is positively charged. Okay, it is positively charged, and if it's coming direct back, then it is getting repelled. How will it get repelled? If there is a positive charge here, only then it will get repelled, right? Only then it will get repelled, because there are some electrons, small electrons. Alpha particle has a bigger mass than electrons, right? So alpha particle, it mostly went straight, it mostly sometimes got deflected at a little angle, but in the center it got deflected right back. So what is happening? What is the case? Then Rutherford and his two scholars made some very important points. They gave some very important observations. They said that they were expecting that all particles pass straight or deflect slightly, right? But they observed that most particles still passed straight, but some sharply deflected, just like we saw, and a few bounced back. Few of them completely bounced back. So what is happening? They are bending, right? They are scattering, they are going through it, and see, few, they are bouncing back, right? If this alpha particle go and bounced completely back, this alpha particle went and this got deflected. Mostly of them passed straight. So these are some of the observations you have to remember, right? These are the three observations you have to remember. First is most of them passed straight. Second is some of them sharply got deflected. And third, some of them, very few, they completely bounced back. Okay, now because these particles are scattering, so it's also called alpha ray scattering experiment. This is alpha ray scattering experiment. Okay, now this kind of failed the Thomson's model. Why? Because according to Thomson's model, this is like a watermelon. Now if I fire alpha particle, first this hole is positive, so it should get deflected from everywhere, right? But note, it is just bouncing back from the center, and somewhere else it's getting a little deflected. So that means positive charge is not uniformly distributed inside the atom. It means, and then Rutherford made a very important observation and a point that this positive charge inside the atom, it is not completely uniformly distributed. It is localized at the center. And it is heaviest at the center. Okay, so he said that according to this theory, atoms have a nucleus. They have a nucleus with a positive charge. They know it's a positive charge, they called it a nucleus. Okay, they have a positive charge and most of the mass surrounded by the electrons. Now they said that, see, there was one more very neat observation in this. They said most of the particles, alpha particles, passed directly. That means most of the space inside the atom, the space inside this atom is what? It's empty, because they neither got deflected, they neither got bounced back, they passed direct. That means they were not influenced by anyone, anything around. That means most of this atom is empty. Okay, most of this atom is empty, and the maximum mass of this atom is at the center where the positive charge is located. So most of the mass is there. The atoms have nucleus with the positive charge and most of the mass surrounded by electrons, and electrons are surrounded around this positive charge. So that was a model given by Rutherford. Okay, it explains why particles can pass through or bounce off atoms and is the basis of our current understanding of atomic structure. So he basically gave the theory that positive charge is not uniformly distributed inside the atom. It is actually located at the center, and at the center only we have the maximum mass of the atom, because all the alpha particles passed straight, so maximum space is empty. So where the mass is located? It is located at the center, but atom is neutral. Okay, so and we know it has electrons. Where are electrons? They are just roaming around. They are just roaming around this positive charge. Okay, and this positive charge is equal to the negative charge of electrons. Done. And this positive charge, they call it as nucleus, and inside them we have protons. Okay, let's study about that. Now what he exactly gave, study carefully. Positive charge is not spread out. Okay, it is concentrated in a tiny dense center that is called our nucleus. Understood? Most of the atom is empty space. Most of the atom is, I am just boxing the main points. Okay, now it is at the center, it is called nucleus. Most of the atom is empty space because most alpha particles passed through it. Right now this nucleus, beta, it is very dense. Okay, holds all the positive charge, it holds all the positive charge and most of the mass of the atom. Okay, now electrons revolve around the nucleus like planets, so it was called as planetary model. Okay, now beta, it was also seen that this nucleus, right, this nucleus, the size of this nucleus is very, very small. Typically we have seen that the size of our atom is 10 raised to power minus 10 meters. Okay, but nucleus, it is 5 times more smaller than the atom. So its mass, its size, so this is the diameter. Okay, so its size is 10 raised to power minus 15 meter, 5 zeros, 10 lakh times smaller or smaller than the actual atom. So that's like, that's, I had the comparison. That's like a pepper grain at the center of a cricket ground. That's how small is the nucleus as compared to the atom. Atom is your cricket ground and the nucleus is small pepper grain, and that pepper grain holds 99% of the mass of the whole cricket ground. Just try to imagine that. Okay. Now this was the whole Rutherford model. So first came Dalton. He said atom is indivisible. Thomson, he said no, I have found electrons. So this is a melon model. So positively charged is completely uniformly distributed. Electrons are embedded as seeds. But then Rutherford came. He did the gold foil experiment and he saw three things. Atoms are passing directly, most of the alpha particles are passing directly from the atom. Some are getting deflected, some are completely bouncing back. That means at the center there is a heavily positive charged thingy, right, inside the atom that consists of most of the mass of the atom, and that thing we called nucleus. It's positively charged, that means protons are there in it, right, and electrons are revolving around the atom. Done. Now they questioned about what are electrons doing. They are revolving, but like how are these electrons revolving? And that is somewhere Rutherford failed to explain. He explained most of the stuff, which is very good, massive respect, but there are some things he could not figure out. Their PhDs, the scholars, could not figure out. That was what, beta? See, a revolving electron is accelerating. You remember motion chapter? We studied that whenever something is in motion, its acceleration is changing. Why? Because direction is changing at every point, right? They are not moving fast, but at every point acceleration depends on direction. It changes with direction, and in circle at every point direction changes. So electrons are accelerating because they are changing direction at every point inside the circle, right? Then that means it should lose energy when they are accelerating, and they don't have external energy source to accelerate them. When we do that rope, we are the ones giving it energy, right? But if you're giving them less energy, it will start to come inside the diameter of the, you rotate a rope, okay, and you slow it down, you will see that the radius was this big, and then it will start getting smaller, and then it will stop. That should what happened to electron, right? There is no external energy provided. If it's just revolving, it is accelerating, so it should like keep reducing its radius and fall into the nucleus, right? It should spiral in and crash into the nucleus, and hence atom collapses. It should not exist at all, right? Atom should not exist at all. But we know we exist, I exist, you exist. Atoms are stable, they are not collapsing. So what is happening? That's where they somehow failed to explain that. So the model was incomplete. Then a new idea was needed. So this is your electron. It is revolving, and it should collapse. And the atom, boom, it should collapse. Right? Now, beta, the thing what we needed was going to come very soon. Okay, now before that there was something Rutherford did, that's the discovery of proton, obviously the positive charge. He said nucleus, positive charge, nucleus is positive charge comes from protons. So we said nucleus has positive charge, but what gives it the positive charge? Protons gives nucleus its positive charge, right? That means much heavier than electrons. These protons are much heavier than electrons, but their charge was same to electrons because atoms have to be neutral. This atom, it has electrons and a positive charge. It has to be neutral. So this positive charge and this electron should be of same charge. Positive and negative should be of same, then only it will neutralize, right? But the mass of this is very greater than the mass of electrons. So that is your proton, same charge as electron, but mass way greater than electrons, right? Now for a neutral atom, again your protons should be equal to electrons. Their charge is similar. So if I have 5 electrons, I should have 5 protons for atom to be neutral. If I have 10 electrons, protons should also be 10 for atom to be neutral. Right? That's the case. That means in helium we have 2 protons, 2 electrons. In sodium we have 11 protons, 11 electrons. So there is a tiny dense positive charge that sits inside the nucleus, that is called our proton. Okay, so the next model actually explains what is happening. Okay, done. Let's see that. Now beta, after this, it was not okay to explain that how electron is revolving around the atom, around the nucleus inside the atom, and we needed a new model for that. Okay, so basically we need some fixed energy levels. That means what? Okay, take it slow. Then came Then came Bohrji. Okay, then Bohrji came and Bohrji said that, listen to me, actually atoms are not randomly rotating around electrons are not randomly rotating about atoms, right? They are actually, beta, they are rotated in fixed circular paths. So if this is your positive charge, then around the atom we have these kind of circles. And in these circles, beta, electrons are revolving. One electron is revolving in this circle, one electron revolving in this circle, one electron revolving in this circle, something like that, so that it's a fixed circle. They are revolving in that, and they cannot leave this path. They cannot leave this fixed circular path until or unless some energy is given in itself. Unless there is a force, unless there is an energy, these electrons cannot leave these circular paths, and these circular paths, beta, these are called orbits, or these are called shells, or very important, these are called energy levels. Okay, energy levels, because each of this circle has a fixed energy. Each of these circles has a fixed energy, and by every circle, see, this circle, let's say, has energy of 1 unit. It has energy of 1 unit. Then this will have 2 or 3 unit, more than 1 unit. Okay, then have 4 unit, 5 unit. So what I'm trying to say, as we go out, energy increases as the shell number increases. Okay, so as we go out, it has lowest energy, it has more energy. Okay, so that is the basic idea of your Bohr's model. The one thing that Rutherford could not explain, that how electron is revolving, it should crash in the nucleus, right? But Bohr said it will not crash in the nucleus because it cannot leave this path. Okay, so it will not leave this path, it will not crash inside the nucleus. Done. So that's what happened. These electrons revolved only in fixed circular path. These are called shells or orbits or energy levels. Okay, these shells are named as KLMN. Why were these named KLMN? So there was this scientist who were like, maybe we are going to discover something more. So from A to K, they left out some things, they left out some energy levels, so that if we discover in the future some new energy levels, we can name them from ABCD, right? But actually they did not, so it is just named as KLMN energy levels. Now this is your first energy level. So the number of energy level, K has 1, L has n equals to 2, M has n equals to 3, N has n equals to 4. Done. So K energy level number 1, L energy level number 2, M energy level number 3, N energy level number 4, and so on. Okay. Now beta, K, that is n equals to 1, is your closest to the nucleus. This is your nucleus, right? So the first shell just outside the nucleus is your kth, then L, M, N with an n, 2, 3, 4, and energy rises. Okay, energy rises as you move outwards. Done. In an fixed shell, an electron does not lose energy. So when electron is revolving in that fixed shell, it cannot lose energy, because if I'm rotating it in one speed, in one, I'm giving a particular force to it, it cannot lose energy and fall, right? It is not allowed to lose that shell. Done. So rather have a definite amount of energy. So it has a definite amount of energy which it cannot lose, and hence it is keep on rotating in one single fixed circular path. Understood? Then beta, this stationary state means this particular circle, this stationary state is called, it explains the stability of atom, because atoms are not, electrons are not collapsing, and there is a positive charge, all the electrons are there, number of electrons, number of protons, number of negative charge, positive charge is same. So it kind of explains the whole, atomic stability of an atom. Okay, now there was one thing, absorbing and releasing. So this electron, however, can, maybe I provide some outside energy to an electron sitting here. Okay, so it can absorb this energy and it can move to the higher energy level, because see, this energy is 1 unit, this energy is 2 unit. Now I give 1 unit of energy more to this electron. Okay, now this electron has how much energy? It has 2 units of energy, but this shell can't have 2 units of energy, so it will move to the upper shell with more energy. Okay, and similarly it can release energy as well, it can release energy and it can go down to the lower shells as well. Not that much important topic, but still if you just remember this point, it will be easy to do some weird questions that CBSE might give you. Okay, so it jumps shells only by absorbing or releasing energy, a fixed packet of energy. So going from here to the second unit, we need just some fixed 1 unit of energy. Okay, by absorbing that only it can move to 2. If it absorbs 1.5 energy, it cannot absorb 1.5 energy, because there is no shell with energy 1.5. Okay, that it can go to. It needs to have the same code. The electron and the shell, they need to have same energy to rotate in that shell. Understood? Okay, that's the whole point of Bohr's model, and it explained very lovely that how the atom is not collapsing, right? Also, it explained atomic spectra. You will learn it after some time, do not stress on this. And it introduced the concept of quantized energy levels. Quantized energy level means all the energy levels of the shells. This shell K, okay, this L, this M, this N. It means that this whole shell has one single energy that is different than the energy of this L shell. This whole shell has one single level of energy, one single amount of energy. Then M has one single amount of energy which is different than all other shells, and we term it as quantized. That means their energy is fixed. It has a fixed number. Okay, and it cannot be same as the others. Okay, that is called quantized energy levels. Then this is the basically thing why KLMN and not ABC. So physicist Barkla named the first X-ray line as K. You will study why it is called X-ray line, leaving room for an earlier series which was never found. So Bohr kept that same notation. Okay. But beta, it also had some limitations. It was limited to hydrogen atom only. It was limited to hydrogen atom only, which had only one electron. So it just explained that model clearly. Okay, then it couldn't account for the behavior of multi-electron atoms. Now multi-electron atoms which had more electron in their shells, it could not explain why they were behaving in a different way than the atom which had only one electron, right? And it did not incorporate the wave-like nature of electron as well. It just said that electron is a particle and it is revolving around in a fixed circular path. It did not take into account what it will do to the wave nature of electron. Okay, however, we are studying till here only. You don't have much in your syllabus. However, a lot more scientists came and we studied a lot more about lots of depth in about SBDF, orbitals, molecular orbitals, wave functions or something like that, but that's not in your syllabus. Okay, it is here till here. Okay, so this was the basic juice of atomic theory. What came first? Who came first? We have, yes, so first came Dalton. Okay, he said that atom is indivisible, right? But he was wrong. So then came who? J.J. Thomson, right? J.J. Thomson, he said that atom is like a melon model, and the one thing he did that was very beneficial was he found out electrons, right? He discovered electrons, right? Then came Rutherford. Then came Rutherford and his two PhD scholars, whatever you want to call, and they gave that the question why atoms don't collapse. They answered this question, right? And they gave fixed energy levels, and electron is rotating in fixed energy levels. Okay, they did not answer this question. Okay, they could not answer why atoms don't collapse, because there is a positive charge at the center. That's what they gave, and the heavier the mass of all the atom is concentrated on this single point, and there is an atom and electrons are revolving around us. But they could not explain why atoms don't collapse. As electron is accelerating, it should lose energy and collapse inside the nucleus, but it doesn't. Why? That is then given by what? Bohr, right? Neil Bohr, he said that electrons are revolving in a fixed orbit around the nucleus, and they all have fixed energy levels. They are called K, L, M, N. L has more energy than K, M has more energy than both L and K, N has more energy than M, L and K. Done? Okay, great. So this was basically your atomic theory. One part that was then figured out that when you see periodic table and when they weighed the atoms, okay, they weighed the atoms, that hydrogen has 1 electron, 1 proton, okay, and it is positively charged. Helium beta has 2 electrons, right, and 2 protons, okay, that should be great. This is neutral. But what they couldn't discover, that its mass should be 2 times, right? Here we don't take the mass of electrons. See, the mass of electrons is simply 1.6. What is the mass of electrons? I forget this every time for some reason. Have I written it? Okay, let's say the mass of electron is 9.1 10 raised to the minus 31 kg, I think. Yes, this is the mass of electron, right? Minus 31, okay, and proton has a bigger mass than that. Now, so we neglect the mass of electron. So according to that, if mass of hydrogen is 2 units, 2 kgs, not 2 kgs, 2 units, let's say, then the mass of helium should be if it has 1 unit, okay, one protein, if it has mass of 1 unit, then helium should have mass as 2 units, because it has 1 proton, it has 2 proton. And similarly, then third element with 3 protons should have mass 3 units, 4 proton, it should have mass 4 units, right? But that was not the case. This was not the case. When we actually weighed the elements, we found out that this has mass 1 unit, but it should have 2 times the mass of hydrogen, but the mass of helium was 4 times the mass of hydrogen. It was 4 times the mass of hydrogen. How come? It has 1 proton, it has 2 proton. How come the mass is 4 times? Mass of all protons is same, but how come the mass is 4 times? That's where Chadwick G come. Okay, Chadwick G come, and he says that actually you are missing one thing. What you are missing, that inside this atom, a perfect circle. Okay, inside this atom we have a nucleus, and we said that there are electrons here. Okay, there are electrons here in fixed shells, rotating in fixed shells. Okay, electrons here, and we have more electrons here, and this is your nucleus. This is your nucleus. Okay, done. But tell me one thing, it has 1 proton and it has one mass, but helium has 4 times the mass. Then James Chadwick came and he said, actually there is not just proton inside this nucleus. There is not only proton inside this nucleus, there is one more thing called neutron. So he said that the nucleus is actually made up of protons, those are your positively charged particles, plus it is made up of neutrons, which are neutral. They are neutral. They don't have any charge on it. Neutrons, they don't have any charge on it, but they have mass. Okay, that is why when we move from hydrogen to helium, in helium we have 2 protons, but we also have 2 neutrons. So charge is same, but because neutron is neutral, it does not add up charge on the atom, but they have mass equal to the proton, right? So they adds up the mass to the atom. Okay, so what happened? What did he say? That the puzzle was that helium has 2 protons, okay, but 4 times the mass of hydrogen, not just 2 times. So what else is giving it the mass? So James Chadwick, again a very interesting thing, he was a student of Rutherford. So Rutherford has a big hand in the whole atomic theory, right? He discovered that neutron is actually made up of, it is equal to mass of proton. Okay, now but it has no charge. So inside the nucleus we have neutron plus proton. Neutron has mass equal to proton, but it does not have any charge. So it does not provide charge to the atom, but it provides mass to the atom, and we define it with a symbol N. Okay, now this neutron sits in the nucleus of all atoms except hydrogen. It does not sit in the nucleus. Okay, now that means the total mass of the atom is equal to the mass of proton plus the mass of neutron. Okay, because electron's mass is negligible. Okay, then beta, there is one more thing, that like charges should repel. Okay, neutrons space protons out and strengthen the nuclear force. Okay, so one more thing happened, that they are saying that inside the nucleus, okay, this is your atom, this is your nucleus, there are lots of protons now. Okay, for five okay, protons inside this nucleus, there should be so much repulsion, right? All the positive charge, this together, oh, there should be so much repulsion. But what happens, there these neutrons come, okay, and they space themselves in between these protons. They space themselves in between these protons, reducing the repulsion and increasing a charge called increasing the binding force called nuclear force. It helps to bind these particles together. Okay, so nuclear force, because of these neutrons, atom is actually stable. Because of these neutrons, positive protons don't repel each other inside that nucleus. Okay, beta, understood? Okay, now moving on, we have a very interesting thing. Okay, we have something here, light atoms have equal P and N, heavier ones need more neutrons. Yes, so one more thing you'll see, as you move towards heavier atoms means I have 50 protons inside this nucleus, 50 protons inside this nucleus. Okay, now the repulsion force will be too much, then they have more number of neutrons than protons. In heavier elements, the number of protons and neutrons are not same. Number of neutron is more than number of protons, so as to reduce the repulsion and increase the nuclear force, the binding force. Understood? Okay, next beta, let's move on to a very important point. So this is where your atomic theory ends. Okay, this is where your atomic theory basically ends for now. Okay, for 9th and 10th. Okay, now we see so many elements. This is like the phase 2 of this chapter, moving into the elements part. Now we know we find so many elements in the nature. There is sodium, there is carbon, there is iron. Okay, everything is made up of different elements. Everything has different kind of atoms, right? So let's talk about all these. So by 1869, remember 1869, only 69 elements were found. At that time, only 69 elements were known to be found naturally on Earth. Mostly they were. But today we have 118 unique chemical elements. Some are artificially made, but they are unique. That means the number of electrons in their atoms, the number of protons in their atoms is unique. They are not similar. Okay, the atom through which this pen is made and the atoms through which this pen is made, this book is made, is not the same, right? They are they are different. Correct? But we have 118 different atoms in which the arrangement of electrons, the protons, their number is different. Right? Now, for all those 118 elements, Dalton, 1803, he suggested to have some pictorial symbols. He suggested to have some pictorial symbols. What are those pictorial symbols? Look at this. Okay, he said if we specify, if I have to write hydrogen, I can write like this. If I want to write carbon, I can write like this. You shade it. Okay, if I want to write oxygen, you can write this. If I want to write phosphorus, you like write this. But you tell me how hard this is to remember, right? How hard this is to remember all these symbols. Really hard. Okay, so it was not very useful. It was not very good. Right? So in then 1813, Berzelius came and he said he gave letter symbols. He gave letter symbols from Latin names. We have Latin names of literally everything, but we have Latin names of elements as well. So he said that we can name these elements according to their Latin names. So we have sodium. Right, we have sodium, so we write it as Na. Why not So? Why not S? Because we have sulfur, so we have need to differentiate. So we take from natrium, the Latin name of sodium, we take the symbol Na. For potassium, K, that is kalium. Ferrum for iron, that is Fe. Copper, Cu from cuprum. And similarly, all those things, argentum, aurum, plumbum and hydrargyros. Okay, that is your mercury. Okay, so these are some of the elements we named based on their Latin names so as to not confuse with other elements. Okay, so these were some of the elements, but bacha, we have a new a small, literally small topic just as IUPAC names. Okay, so these names IUPAC, it's a global level chemistry, let's say body, okay, which names all these elements so that all over the world, whoever scientist is doing something, they are using the same thing with the same name. They are describing it in their papers in the same, with the same name, okay, to avoid any confusion. Then now some of the rules are there. First letter capital, second if any is small. So hydrogen, Al, aluminium, we don't write aluminium as Al, capital Al. See, these can be small things but very important. We always write aluminium with small l, not with capital L. We write CO for cobalt. We don't write CO, okay, that is carbon monoxide. Okay, so we don't do that. Okay, we have to be very careful. Some use a later letter, that is chlorine and Zn. Okay, done. Okay, then we have this, some from Latin, Greek, German, ferrous. Okay, this is mercury, this is your what, tungsten. Done. Then we have symbols. These symbols are universal but they understood all across all languages. These are understood across all languages. Even in German you say that what I want some aluminium, they'll give you aluminium only. Okay, okay. Next beta, after this a very important topic, like first of all, these are the symbols of all the elements that are there. The first 20, more than 20 elements are written here, so you can clearly see aluminium Al, argon Ar, barium, boron, bromine, calcium, carbon, chlorine, cobalt. We have copper from cuprum, fluorine F, gold aurum from Au, hydrogen H, iodine I, iron ferrum from Fe, lead plumbum, so we write it as Pb, magnesium Mg, neon Ne, okay, and similarly all these. Done. Next beta, let's move on to a very important point, that is your atomic number and mass number. See, now you have seen atom, right? You have finally understood about the atom a little bit, right? And we know there is a positive charge at the center, and we know there are then multiple circles around it, and we will know that electrons are revolving around these circles. Okay, now I told you there are 118 unique elements that exist. Okay, we have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, and all other elements. Okay, now beta, this has only one electron in it, one proton. This has one electron, one proton, and this has, okay, this has two electron, two proton, and two neutron. Electron, proton, neutron, right? It has now 3 electron, 3 proton, 3 neutron, right? So this is something we know about, right? But now these are atoms, right? This is an atom. This is an atom. So we give it according to the number of electrons, protons, neutrons we have. We give it a name called atomic number, so that we can differentiate the properties of each atom. Sodium has different number of electrons and different atomic number. Potassium has different number of electrons and different atomic number, right? So what is this atomic number? This atomic number is bacha number of protons. Where did this F go? Number of protons inside that atom. Now we know one more thing, that number of proton is always equal to number of electron. For now, number of electron, number of protons are same. That's how our atom is neutral, right? In a neutral atom, number of proton is equal to number of electron. So atomic number is equal to number of proton in that atom, but is also equal to number of electrons in that atom as well. Done? Understood? Atomic number understood? Let's look into it. What is it? Atomic number written by Z or Z, whatever you want to call it, right? Number of protons, it fixes the element's identity and chemistry. So it's basically number of protons present in that atom. A neutral atom, we have number of protons equals to number of electrons. So this Z is equal to number of electrons. That's the first thing we have to study. Okay. Now beta, in this atom, we also know that we have protons and neutrons as well. We have protons and neutrons as well. And both of these proton and neutrons, they exist inside what? They exist inside this nucleus, right? This nucleus has proton plus nucleon. So together these protons plus nucleons, protons and neutrons together are called as nucleons, something that exists inside the nucleus. Okay, now beta, together, see, we have one more thing called mass number. Now see, all the mass of the atom is at the center inside the nucleus. Okay, so we call it as mass number, and every atom will have different mass number. 2 plus 2 4, 3 plus 3 6, right? So they have different mass numbers, so we give them a different, they have different mass, so they have different mass numbers, and this mass number is equal to the addition of protons, number of protons plus number of neutrons inside the nucleus, inside the nucleus. So this is beta your mass number. Okay, now one more thing you have to learn is how to represent an element. We have 118 element, and we want to represent that in such a way that we get to know their atomic number, their mass number, proton, electron, neutron, everything in one simple symbol or thing, right? So what we do, we write it as this. Okay, look very carefully. This is an element. Okay, this is X. Okay, this X beta is your element: carbon, sodium, potassium, magnesium, aluminium. Okay, and on the upper side, over its head, we will write its mass number. Now one more thing, this mass number is depicted by A, your atomic number is depicted by Z. I know it can be a little bit confusing, but I'm telling you a trick. Okay, just bear with me for 1 second. Now this mass number is depicted at the top, that is A, and this atomic number, that is your Z, it is depicted in its foot. Okay, but how will you remember this? You just have to remember one thing. Okay, you just have to remember that atomic number is depicted by Z and mass number is depicted by A. Okay, now how do you remember it? How do you remember it? It's a cheat trick. Okay, what you do, you write it as mass number, you write it as atomic number. Okay, now this is ma, your mother, mama, mummy in all languages, right? Amma, right? So this is M-A, right? Your ma, mummy, amma, I, whatever you call your mother, but this is ma. We all know what ma is. Okay, so you write it ma. You write an element X, you write ma. Just one thing that you have to do. Now we'll figure out, okay, mass number is depicted by A, atomic number is depicted by Z. Okay, mass number is proton plus neutrons, atomic number is protons or number of electrons. Done? Understood? Okay, so let me just write the symbol of helium. Helium. Now helium has 2 protons, it has 2 electrons and 2 neutrons. Done. So here should be mass number. Mass number is what? Protons and neutrons. So protons and neutrons, protons plus neutrons, 2 plus 2, that is 4. Okay, and number of protons or number of electrons are either 2, so it will be 2. So basically this is the symbol for helium. Understood? Basically this is the symbol of helium. Now we have, okay, let's write about carbon. So this is 1 2 3 4 5 6 7. So let's write about carbon. So carbon beta, it has 6 number of electrons, 6 number of protons, 6 number of neutrons, right? 6 number of neutrons. So what will happen? We'll write ma, M-A. Okay, mass number. Mass number is what? Proton plus neutron. And this is your proton or electron. Okay, here you have to add, here you don't have to add. Proton plus neutron, 6 plus 6, that is your 12. So carbon is 12. Okay, and atomic number is what? 6. So this is your symbol of carbon, which depicts that the mass number of carbon is 12, atomic number of carbon is 6. Done? Understood this point? So beta, mass number is what? Your protons plus neutrons, and these are collectively called nucleons. Electrons mass is negligible in this count. Okay, so A is the number of protons plus number of neutrons. Okay, done. Now we have to do one more thing after this. We are given with a let's say a symbol. Okay, we are given with, let me see, We wrote that down, right? Yes. So let's say nitrogen, or let's say I give you anything. Okay, I give you any literal symbol, that is A, and I'll give you that this is 7, okay, and this is 14, and they will ask you what is A. Okay, then you have to make a table. Okay, you don't have to make a table, but you have to make a table because I'm telling you it's just easier. Okay, you write number of electrons, protons and neutrons. Done. You make 3 columns and then you write. See, here we have what are number of protons. Number of protons equal to number of electrons. Now you write the exact symbol, that is your X, Ma. Ma, mass. This is your mass number, which is depicted by A. This is your atomic number depicted by Z, right? This mass number is equal to proton plus neutron. This atomic number is equal to either number of protons or number of electrons. So beta, this is atomic number. This is equal to what? Proton or electron. So it has 7 number of electrons, 7 number of protons. Done. Then we come to neutron. Okay, actually neutron is not given, right? This is this thing 14, it's mass number, and mass number is total. So we have 14 equals to proton plus neutrons, but proton is given. This is number of protons, this is atomic number is number of protons, right? So proton is 7 and this is 14 and this is number of neutrons. So can you find number of neutrons now? That is 14 minus 7, n equals to 7. That means it has 7 neutrons. It has 7 neutrons. Ma'am, why are we finding this? Everything is coming same. We just find out one and we'll write everything same. There is something you will learn, isotopes, isobars, in this lecture only in few minutes. So stay with me. I will tell you why are we making this diagram and why are we learning all this. Okay. Okay. For right now, we are clear with your atomic number and mass number. Done. Atomic number and mass number, all of this is clear. We have X, the symbol above is A, that is your mass number. The symbol down there is Z, that is your atomic number. Atomic number is equal to number of protons, mass number equals to number of protons plus number of neutrons. Okay. Okay. Next beta, we are moving on to a very important thing, that is your filling the shells. We learned that this is your atom and these are all the shells inside the atom, and this is your nucleus. This is your nucleus inside the atom. I'm just making it with a different color so you can see. Right? Now beta, whenever we talk about filling the shells, this is your K shell, this is your L shell, this is your M shell, this is your N shell. Understood till here? And now here we know that K, this is N equals to 1, N equals to 2, N equals to 3 and N equals to 4. Okay, done till here, no doubt. Now, why am I telling you all this? Now, this is Bohr-Berry rules. Bohr, the one who told that these shells are fixed, also gave the thing where he told how many electrons are there in these shells. Okay, so let us see this. Now, basically, he gave a formula called 2n square. Okay, where this n beta, where this n was your number of shell, right? Now we know we studied K, L, M, N, right? Now for this n was 1, this n was 2, n was 3, n was 4, right? So all this we have studied, right? Till here clear? Now see, one thing that you have to remember. Let me make a box, it clears everything. Okay, now see, what is the formula? 2n square. This is what? This is number of electrons in that shell. number of electrons in that particular shell. Okay, now see, this is the kth shell. It has n equals to 1. So I will put in this formula n equals to 1, that will 2 into 1 whole square, and it will be simply 2. That means in K shell you can fill maximum electrons as 2. This is the maximum number of electrons. Maximum number of electrons. Okay, then we come to L equals to 2. Its n is 2. Right, so in this here I will fill 2 into n is 2, right? So I'll fill 2 and square. So that will be what? 2 into 2 square is 4. 2 into 4 is 8 electrons. So in the L shell beta, you can fill 8 electrons. You have to fill 8 electrons. Done. Then coming on to M. Okay, now M has n equals to 3. So 2 into 3 whole square. 3 into 3 is what? 9. 2 into 9, 18 electrons. Done. Then we have n, where n equals to 4, right? So 2 into 4 square, that is 32 electrons. Let's just go back and see what's it's written. Now beta, see, maximum electrons in a shell is 2n square. Okay, K is 2, L is 8, M is 18, N is 32, right? This outermost shell holds at most 8 electrons. The first shell, maximum 2. That means this is your first cell. So there can be only 2 electrons in this shell. There can be only 2 electrons revolving in this shell, not more than 2. And then this is your second shell. We have L equals to 8 electrons. So here 1 electron, 2 electron, 3 electron, 4 electron, 5 electron, 6 electron, 7 electron, 8 electron. Only these can be revolved, not more than 8. Then in M we have 18th, right? So fill the stepwise, first inward to outward. So first we have to fill K, then L, then M, then 8. Done beta. So K, L, M and N, a shell fills only after the one before it is complete. So if the L does not have 8 electrons, you cannot move to the M shell. You cannot put an electron in M shell if L only has 7 electrons. After it is filled with 8 electron, the next electron will go and will not sit in the L shell, it will go in the M shell. Okay. And this arrangement beta, it is called electronic configuration. Okay, this is called electronic configuration. So see, oxygen has 8 total electrons. This is 8 atomic number. Atomic number is number of protons and electrons, or number of electrons. So we fill in K shell, we will fill only 2 electrons. Then in L shell, all the remaining ones, we have 6 electrons. 6 plus 2, 8. Right? Then we have 11 atomic numbers, so we fill 2, okay? And then in the next shell, we can fill maximum 8. We filled 8 and 1 electron is remaining. It will not go in the L, it will go in the mth shell, right? And then chlorine, we have atomic number as 17, number of electrons 17. So first we fill the K shell as 2, L shell as 8. Now all the electrons will go to M shell. Right? Similarly, argon, we have 2 and 8 in the L shell, 8 in the M shell. Done. Then similarly, magnesium. Let's do for magnesium. We have magnesium, atomic number is what? Its atomic number beta, it is 12. Right? So it has 12 number of electrons. Right? Now, in magnesium, I can fill the electrons in shells. Those are what? K, L, M, N. Right? So I will fill 2 in this K. Okay, 12 out of 2 are filled. What are the remaining? 10. Now out of those, 8 will be in the L. What is happening? 8 is in the L, right? And then the remaining 2, 2 plus 8, 10. We have total 12. Remaining 2, they will go into M shell. Done. And similarly beta, we have configuration for all the electrons. Now if you want to make this model, what will you do? You have a one, we have 3 shells, K, L, M. So we will make 3 shells, right? This is your nucleus, and inside that we will have electrons, 1 electron. I will depict electron as a dot. Okay, let me depict electron as a dot, it's much easier. So 1 electron, 2 electron, 1 2 3 4 5 6 7 8. Okay, they will adjust themselves. Then the other 2 electrons, these remaining 2 will be in M shell. So this beta is your K shell, L shell, M shell. N equals to 1, N equals to 2, N equals to 3. Understood? And similarly, you can draw this for all the atoms in your periodic table literally. But for right now, these are the first 18 elements. So you see, hydrogen has 1 atomic number, there is 1 electron. It has 2 atomic number, 2 electrons in the first shell. Now in the first shell, only 2 electrons can be there. If the third electron comes, it goes to the third shell. It goes to the second shell, right? This is your K shell, this is your K shell, this is your K shell. The third electron comes, it goes and sits in L shell, not in the K shell. Now next, beryllium 2, boron 3 in the L shell, carbon 4 in the L shell. Okay, similarly in this the electrons are increasing. It will increase till they are 8 electrons. 1 2 3 4 5 6 7 8. Now the 9th electron will go where? In the next shell. In the next shell. So 1 2 3 4 5 6, okay, 7 8. And this argon, if you see it, K shell has 2 electrons, L shell has 8 electrons, M shell also has 8 electrons. Done beta? Done beta? Now this is your basic atomic structure. They can ask you to make the atomic structure of neon. How will you know? Beta, first you have to remember the atomic numbers of first 18 elements, first 20 for safe side at least in your class. Okay, so hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, and your silicon, phosphorus, sulfur, all these atoms you should remember their names with their atomic numbers at least. Okay, then only you will be able to do the configuration. You should know how many electrons are there in chlorine. Only then you will be able to fill this atomic structure, right? So that's the thing you have to do. Okay, now moving on to a very important thing and a very interesting thing, that is beta, you have seen that in there are so many other elements, there are so many other things in nature which are not made up of single element. We have acids, right? The acids are HCl, made up of what? Made up of hydrogen and chlorine, right? So these are two different atoms combined together, right? We have water, we have H2O, it is made up of 2 hydrogens and 1 oxygen, right? These are two different elements combined together. So how are they combining? Why is 1 oxygen sitting with 2 hydrogen but 1 chlorine is sitting with only 1 hydrogen? What is this? What is this? Okay, so this is beta, something called as combining capacity or valency. We call it as valency. Now see one thing, whenever we fill our K, L, M, N shells, what is happening? Okay, we have 2 and we have, see, for hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. Okay, now see, it has atomic number 1, so 1 electron is in K shell. Atomic number 2, 2 electrons is in K shell. Atomic number 3, then have 2 electrons in K shell, 2 electrons in K shell and 1 electron in L shell, 1 electron in L shell. Then it has 4, it has 2 electrons in K shell, 2 in M shell, then 2 and then 3, 2 and 4, 2 and 5, 2 and 6. Until this it is clear. Now you tell me one thing, what are the maximum number of electrons this L shell can have? It can have 8 electrons. It can have 8 electrons. Right? Now beta, if this L shell loses 1 electron. Now see, why I am saying it has 8 shell, whenever this is called duplet. This is called duplet because it can have 2 electrons. This is called octet. It can complete its octet with 8 electrons. Okay. Now beta, whenever it has 1 electron, it has 2 electrons, it is not stable. It wants 8 electrons or it wants 0 electrons. See, hydrogen has 0 electron here. Okay. Helium, the duplet is full. It is full and it is completely empty. So it is stable. This helium is stable because it is filled its duplet and there is nothing. But lithium is very, it has anxiety. It only has 1. It wants 8 or 0. So what is it easier to gain 7 electron or just lose 1? It is easier to lose 1 electron. So it loses 1 electron. Okay. And it becomes stable. It becomes stable after losing 1 electron. It loses what? It loses 2 electron. Okay, it loses 3 electron. First, leave this empty for now. Now come to this 5 electrons. Is it easier to gain 3 electrons and complete its octet? It needs 8, right? Is it easier to gain 3 electrons and complete the octet or lose 5 electrons? It is easier to gain 3 electrons, right? It is easier to gain 3 electrons. So it will gain 3 electrons. Okay, it will gain 2 electrons, and similarly the next element, it will be 2 and 7, it will gain 1 electron, right? So what is happening? This is losing 1 electron. So it is its valency, that is +1. Whenever something loses electron, it gets positive charge. Whenever it gains electron, now you use some common sense. Electron is negative charge, it is gaining electron, so it will become negative, right? It is losing electrons, so negative charge is going out from the atom. It was neutral, negative charge went out, so the atom became what? It became excess positive, so it will become positive. Gaining, it will become negative. So its valency, the valency of lithium is what? The valency of lithium beta is what now? It is +1. The valency of beryllium, now it is losing 2 electrons, so +2. It is losing 3 electrons, +3, losing now 4. We'll study. It can lose, it can gain, but it chooses to share the electrons, and hence covalent bonds, which we will study in carbon and compounds chapter later. Okay, next, this has valency as -3. It is gaining 3 electrons, -3, gaining 2 electrons, -2, and similarly the next one will have gaining -1. So this is beta the whole concept of valency, the combining capacity. Okay, now studying about combining capacity a little bit. Combining capacity, yes. Here, okay, so beta, what I was talking about, right? Water. In water, oxygen combines with 2 hydrogen atoms. So the combining capacity of oxygen is what? It is 2. One oxygen can have 2 hydrogens. So the capacity of oxygen is what? 2 hydrogens. So it can combine with 2 hydrogens. Its combining capacity is 2. See, in NH3, wait, I just knocked off my stylus. In NH3, see, in NH3, N is having 3 hydrogens. So its combining capacity will be what? Its combining capacity will be 3, right? It has 3 hydrogens. Its combining capacity is 3, right? Why do nitrogen has 3 combining capacity? Why do nitrogen has 3 combining capacity? Because it has 3 valency. Hydrogen has 1 electron. It gives 3 hydrogen atoms give 3 electrons to nitrogen. See, hydrogen has 1 electron, right? And it can gain -3, and it is +1, right? It can gain electron, lose electron, so it is easier to lose electron actually. Okay, so this hydrogen gave nitrogen 1 electron, this hydrogen gave nitrogen 1 electron, this hydrogen gave nitrogen 1 electron, and nitrogen can gain 3 electrons, right? Nitrogen can gain 3 electrons. It gained 3 electrons from 3 atoms of hydrogen, so its combining capacity is 3. Understood? Somehow understood? Okay. Similarly with magnesium. Now magnesium is 12, right? Magnesium, look carefully, magnesium atomic number is 12. Okay, so KLM. Now this is 2, this is 8, 2 plus 8 10, and it has 2 electrons in the M shell, so it will clearly lose these 2 electrons. It will lose 2 electrons, so its valency is what? Its valency is +2. It can lose 2 electrons, and it lost these 2 electrons to chlorine. It gave these 2 electrons to chlorine, and hence combined with 2 chlorine atoms. Okay, each of the chlorine atom took one of its electrons, okay, and they combined with magnesium. Okay, they did a trade. Okay, so magnesium has 2 combining capacity. Okay, combining capacity of nitrogen is 3, magnesium is 2. Now talking about that, this is basically what happens, right? Now sodium has 2, 8, 1. It has 11 atomic number, right? So the shells are 2, 8, 1 KLM, right? So it loses 1 electron and it becomes sodium ion. Now if it loses 1 electron, so negative is going out, so the rest, the remaining one is positive. That's why sodium ion has a positive charge on it. Similarly oxygen. Now oxygen is 2 and 6 with atomic number 8, so it can gain 2 electrons to complete its octet to make it 8, so it has 2 negative charge on it. If you have seen, right? So it gains 2 electrons, and oxide ion. Now outer shell has 8 electrons. Here outer shell has what? It loses 1 electron, the shell completely goes away, and it has one lesser shell. Okay, that is the basic function of valency. Just go through what I have written so much. Okay, now valence shell is your outermost shell. Why do we call it valency? Because beta, we studied about these cells, right? KLM, right? KLM. Now if the last electron is in M shell, so this is your K, this is your L, this is your M. Here the last electron is in M shell, right? So M is your valence shell. That means the last outermost shell. Here we just have 2 shell, KL. So L is your outermost shell. Okay, here we just have 1 shell, that is K. So K is your outermost shell. So in whichever shell we have the last electron, bacha, that is called the valence shell, and the electron present in that outermost shell, it is called valence electron. Done. A full octet, 8 electron, okay, 2 for helium, and that is stable and unreactive. It is stable, it is complete, it is chilling. I have everything, I don't want to give anything, I don't want to take everything, don't disturb me. Okay, then if it is incomplete, if it has 5, 2, 3, 4, not 2, okay, 5, 4, 3, maybe anything, so it is reactive. It wants to either take 2 electrons or give 2 electrons. It wants to react with something, right? And valency beta, the number of electrons gained, right, and the lost or even shared in case of carbon to complete its octet. right? This is what we studied, right? The number of electron it is gaining, 3. So 3 is its valency. 2 is its valency. Either it's losing or gaining or sharing. Carbon's valency is plus minus 4 because it can gain the electrons, lose the electrons, or share the electrons, whatever it likes according to the next element, the element that is in front of it. So that is why it is called valency. Okay beta, so if valency is less than 4, valence electrons, the valence electrons are less than 4, 1 2 3, it's easier for them to lose, right? So they will lose electrons. Like sodium, it will lose 1 electron, valency is 1. 4 electrons, more than 4 electrons, 5 6 7, it is easier to gain electrons, so it will gain electrons. Just like oxygen, it gains 2 electrons, valency is 2. Carbon, which has equal to 4 electrons, it will share the electrons, and its valency is 4, right? So combining capacity beta, the number of H or Cl atoms, one atom combines with HCl have capacity of 1. Okay, so this one atom of hydrogen combines with one atom of chlorine, so they both have a combining capacity of 1. In H2O, O joins 2 hydrogen, so the capacity of oxygen is 2. Understood? Okay. Atoms with full octet, those are noble gases. Neon, argon, they don't react. Whenever we do some experiments, right, and we need a inert environment, that means we do not need any free electrons, free positive ions in that environment, we put inert gases in them. We call them inert gases because they don't react with anything, right? So they are stable. Do they still try to gain or lose electrons? No, they do not, because their octet is complete. They are chilling and relaxing. Okay. Next thing beta, we are done with valency as well. Two most important topics are left, that is your isotopes and isobars. A little bit confusing, but don't worry, your Aditi Ma'am is here. Okay. Now beta, see, isotopes. Now beta, what is happening in this whole earth, in this whole world? We have hydrogen, okay, and we figured it out that hydrogen has 1 proton, helium has 2 protons, then lithium has 3 protons, carbon has this 8 valency, okay, 6, sorry, it has 6 atomic number, so it has 6 number of electrons. Oxygen has 8. Okay, great, fine, we are chilling. But earth is like, no, I'll give you so many things. So what we see actually is there are some elements which have same atomic number, that means same number of electrons, number of protons, but different mass number, that is the number of neutrons in those atoms are different. That means, let me tell you, this is protium, okay, this is hydrogen, this is deuterium. Now this is hydrogen, but it has only 1 proton, 0 neutron and 1 electron. It has 1 proton, 0 neutron and 1 electron. Done. It has 1 proton, 1 neutron, 1 electron. This is also hydrogen, but a different form of hydrogen. Now tritium, this also has 1 proton, 1 electron, but it has 2 neutrons, and this is called tritium. This is also hydrogen, another form of hydrogen. Okay, so what do you see? Protons and electrons are same. Protons and electrons are what? Atomic number. So atomic number, that is your number of protons, or your number of electrons. These are beta same. These are same, right? But number of neutrons, number of neutrons beta, those are different. Now how will this impact? Do you remember we wrote a very good symbol, that was your very good symbol. Okay, let me write it here. Done. Now we wrote it a symbol X and we wrote it Ma. right? Now A, here your M is your mass number that was depicted by A. A is your atomic number depicted by Z, right? That is your atomic number depicted by Z. Now beta, this mass number was an addition of proton plus neutron. This atomic number was either your proton or your electron. Either your number of proton, number of electron. This was, however, the addition of number of protons plus number of neutrons. Now you tell me, number of protons or number of electrons are same. So this will not impact. This thing, it will remain the same. It will remain the same. But mass number, protons are same, neutrons are different. Here we have 1 neutron, 2 neutron, 2 neutron, 1 neutron, 0 neutron. So if neutrons are changing, that means mass number is changing. So mass number will be different. It will be different. That means we have 3 kinds of hydrogen. How will you write it? Protium, deuterium, tritium. Okay, we have 3 hydrogen: protium, deuterium, tritium, right? Now these have same atomic number, that is 1 electron, 1 proton. So they have same proton, same electron, right? But here we have neutrons are 0, neutrons are 1, neutrons are 2. Remember? So here mass number, proton plus neutron. Proton is 1, neutron is 0. So this is 1. Proton is 1, neutron is 1. So mass number is proton plus neutron, 1 plus 1, 2. Hydrogen 1, neutron 2. Proton 1, neutron 2, 1 plus 2, 3. So we have 3 different forms of hydrogen existing in nature, and beta, these are called isotopes. These are called isotopes, whose atomic number is same element. 2 things you have to remember in isotope: same element with different mass number but same atomic number. Same element with different mass number but same atomic number due to the difference in number of neutrons. Understood? This understood? How will you remember this, ma'am? Is there a trick? Yes, there is a trick. You see top, so means top is different. Okay, atomic number is same, mass number is different, mass number is written on the top of it. So top, isotope, top part is different. Okay, so beta, we have atoms of the same element. This is very important. Same element, same protons but different mass number. Don't confuse this A with atomic number. We know atomic number is written by Z and mass number is written by A. So this is mass number. This is your, let me write it, this is your mass number. You will get confused in 1 or 2 lectures, in 1 or 2 revisions, but after that you will get the concept. Okay, now these are called twin atoms, you can call them, and they have different mass number. That means different number of neutrons, because protons are same. Okay, now beta, very important, they have same chemical properties. They have same chemical properties. Why? Because chemical properties are based mostly on electrons, protons, not on neutrons. So it is based on the configuration. Configuration was what? The number of electrons in these shells, number of electrons. If there are 4 number of electrons, it will behave differently. If it has 2, it will behave differently, because it can see, this hydrogen will connect with 1 chlorine, but this carbon, if it has to connect with chlorine, it can go with 4 chlorines, right? It can go with 4 chlorines, right? So this is different. That it depends on electronic configuration. Different physical ones like boiling point, like melting point, it depends on valence electrons. Again, it has 4 valence electrons, it has 1 valence electron, right? Isotopes can be used in very different things. You have to remember this. Uranium 235, used in fuel reactors. Uranium 236 is used in something else. Cobalt 60, cancer radiotherapy, right? And then we have I-131, iodine 131, it is goiter, thyroid treatment. Carbon 14, it's not iodine, it's something else. Okay, carbon 14, dating fossils and artifacts. We can find the age of a tree doing carbon dating using carbon. Okay, we'll study about that, no need to go into it, but in that carbon 14 is used. Carbon 14 is used. Okay, so these are the some functions of isotopes and why do we study them. Okay, now next bacha, we have, based on this, we have something called weighted average atomic mass. Before we go to isobars, okay, see, we know that there are atoms, okay, and each atom has mass based on the number of protons and number of neutrons. Neutrons and protons both are counted in the mass of the atoms. So if isotopes have different number of neutrons, their mass will be different. Okay, understood. But how do we then take their masses? As chlorine, we have chlorine. Okay, so chlorine can exist in certain number of isotopes. It has neutron, let's say 4, or we have neutron whatever 16, then one has neutron 14, then one has neutron 15, just an example. So all of these masses will be different. So how will we take the mass of chlorine if we have to at any point? That is where a concept comes, weighted average atomic mass. What is that? See beta, atoms are weighed in the unified atomic mass unit, that is your AMU, atomic mass unit. Grams are way too much. You imagine the radius, the diameter of an atom is 10 raised to power minus 10 meters. How much will it weigh? Will it be even 1 gram, 0.1 gram, 0.02 gram? No. So we name it as AMU, atomic mass unit. It has its own unit. Okay. Now beta, see, take example of chlorine. There are 2 chlorines in this whole world that exists. One is your chlorine 35 and another is chlorine 37. Okay, chlorine 35, chlorine 37. Now what does that mean? Now this chlorine 35 has 75%. If we found 100 elements of 100 atoms of chlorine, 75 are 35, only 25 are chlorine 37. Okay, these are chlorine 35, chlorine 37. 75% of the chlorine that we found on earth is chlorine 35, only 25% is chlorine 37. So how will we take the weight? So normally what we do, we find 2 types of elements, we average them out, 35 plus 37 divided by 2, 36 unit. But they don't come out to be the same. If it was 50-50%, then we can divide by 2. But now they are not 50-50%. What we will do? Ma'am, we'll do weighted average. We'll do weighted average. So what will we do? We will multiply these percentages with this weight. What will we do? 75% into 35. 35 one is abundant, 75% of abundance plus 25% abundance of 37 chlorine. And this beta is your weighted average. Done. This is your weighted average, and it uses how common each isotopes are. This is 75% in abundance, this is 25% in abundance, and with that we find the exact calculation to be 35.5. So we take the mass of chlorine as 35.5, not 37, not 35, but it's weighted average, not average, weighted average. Very important word. This is weighted average, that is 35.5. 35.5 is no single atom's mass. It reflects the natural mixture of it. Okay, done. Okay, let's move on to the next. We have isobars. Now what are isobars? First of all, the first thing you have to remember, isotopes beta, they were of same element. Isotopes, they were of same element. Isobars on the other hand, they are different elements. First thing, they are different elements with the same mass number. Now let me write it. Let me write this down. You will understand better. Same, let me write MA on this side, okay? So that we can write the actual symbols on this. Mass number is what? Depicted by A. Atomic number is depicted by Z. You remember this yellow and X, okay? MA, Ma is for us. It's a trick, okay? Now, beta, it has same mass number, but different atomic numbers. This number is different. So you tell me, if we have different element, of course the atomic number will be different. If we have different element, of course the atomic number will be different. So you just have to remember one difference between isotope and isobar. This beta is used for same element. This beta is used for different element. Okay, this is used for different element. Same element, that means same atomic number. Of course, each element has different atomic number, so same element will have same atomic number. But this is different element. No two elements can have one atomic number, so they have different atomic number. Atomic number is Z, atomic number is Z. If they have same atomic number, they have different mass number. Mass number depicted by A. If it has different atomic number, it has same mass number depicted by A. I'm telling you how, don't worry, but this is the main difference, and this beta is how you will remember. Understood? Now you will remember just one thing: isotope, same element; isobar, different element. This is the only thing you have to remember. Now let's go back to our isobars. Now they are saying they have different elements with the same mass number, but different atomic number. How is that possible? Okay, let's take an example. Okay, we have calcium and potassium. We have calcium beta and we have potassium. Okay, see, now they are saying they have same mass number. Okay, first atomic number of calcium is, it is what? It is 20, it is 19. Potassium atomic number is 19. Now let's write their symbols. The first thing you have to do is write their symbols. This is calcium, this is potassium. Okay. Now see, you have 20 atomic number. You have 20 atomic number. So I will write atomic number as here as 20. Okay, and I will write the atomic number as 19. Atomic number as 19. Right? Now beta, let's see, these are what? They all have 40 same two nucleons. Now, okay ma'am, wait a second. This is also 40. This is also 40. So they have same mass number but different atomic numbers. Understood? Now from this you can also calculate neutrons. How? Ma'am, this is proton plus neutron and this is neutron. So in calcium, number of neutrons are how much? 40 minus 20. 20. Proton is 20, the neutron 40 minus 20. Neutron is 20. So here 40 minus 19. This is proton plus neutron. Proton is 19. So if proton is 19 plus neutron, total is 40. So neutron will be what? 21. So see, they have different neutrons, different number of electrons, different number of protons, but still their mass number is same. Their mass number beta is same. Right? So they have different atomic number but same mass number because they are different elements. How do we remember this? Ma'am, they are different. The isotope is same element. Isobar is different element. Of course, if something is different, it will have different atomic number. If two elements are same, they have same atomic number. If atomic number is same, mass number is different. Atomic number is different, mass number is same. We have the example as calcium and potassium, 20, 40, mass number is same 40, but number of electrons are 19. It has one more neutron. It has same number of neutron, right? Here we have, what was the example of isotope? Did we study? Yes, we studied hydrogen, plus we studied one more example. We have one more example, that is carbon. Carbon 12, carbon 13, carbon 14. All of these have 6 protons, 6 neutrons, 6 electrons. But this have 6 protons, 7 neutrons, 6 electrons. This have 6 protons, 8 neutrons, 6 electrons. Right? So neutrons are different. If neutrons are different, mass number is proton plus neutron. So mass number is different. Mass number is different. That means atomic number is same. It's carbon. Atomic number has to be same. Right? So we have carbon 12, carbon 13, carbon 14. How can we write this down? I will write it here. And how will we write this down? Carbon, same atomic number, 6, 6, 6. But its mass number is 12, mass number is 13, mass number is 14. Mass number different, same atomic number. Mass number same, different atomic number. Understood? Understood? After this you have to understand. Okay? Okay, beta. Now I guarantee if you study like this, nobody in the world can ever shake your concepts of isotope and isobar. The only thing you have to remember is they are isotope is same element, isobar is different element, and then you build through it. You don't have to cram this. You just remember this. Isotopes are made up of same element. Isobars are made up of different elements. Okay? Okay, beta. The final and the final most is, now this is just theory. So we are done with our whole chapter, journey inside the atom. Quick recap. Dalton came and he said that it was indivisible ball. Atom is an indivisible ball. Then Thomson came. He has positive sphere plus electrons. It was completely wrong. Proved by thin gold experiment, right? Or alpha ray scattering experiment, right? By Rutherford and its scholars. They gave a nuclear model that positive charge is at the center, electrons are revolving around the nucleus, but they could not answer the question that why electron do not fall in the nucleus and why atoms does not collapse. That was given by Bohr, that each electron is revolving in a specific circle, specific circular path with a specific energy, and these were called energy levels. The last shell is called valence shell. The electron in the last shell was called valence electron, and their combining capacity, how much they can give the electron or take the electron, is called valency. Okay? Then bacha, we have one more. It's your quantum electron cloud. This is not necessary for your, but it did came. It's a modern theory. Okay, modern theory. It does not say that electrons are in those shells. It says that electrons are around the nucleus. They are in clouds, and in only those clouds, the probability of having an electron is the most. Okay, and we are still discovering as we go ahead. Maybe you can be the one who discovered where the electron is next. Okay, and I hope you are the one. Okay, so there is one very good line we have. Science advances one step at a time. Okay, one step at a time, driven by curiosity, questioning, and experiment. And this may not be the end, and that's why I only encourage you to ask questions. Whatever you don't understand, ask questions. Even if the teacher is mad about it, why are you asking this question? Maybe they won't know the answer as well, right? Because there are some advancements still going on, but this is for the curiosity, this is for the learning of our human race. Okay, now let's see some questions. What are the key takeaways, beta? Atoms are the building blocks. Okay, now Thomson gave electrons in a positive sphere, Rutherford, Bohr. Now Chadwick was the one who discovered neutron. Remember, there are three particles, electrons, protons and neutrons inside the atom, whereas Dalton said that it can't be divided much. Okay, some of the theory is, if we have full octet, that means 8 electrons in a shell, then it is unreactive and stable. 2 for helium. Valency, electron gained or lost or shared to combine. Atomic number are the number of protons or electrons as well. Mass number is protons plus neutrons, right? Isotopes, isotopes are made up of same element. Same element means same atomic number. Same atomic number, different mass number. Same atomic number, different mass number. Isobars are the reverse of that. Same mass number, different atomic number. Different atomic number, same mass number. Average atomic mass is weighted by isotope abundance. Done. We studied all about that. Now beta, these are some of the questions. If you are curious about these questions, you go ahead in the comment section and tell me the answers of these comments, answers of these questions. We will discuss these in a live session. Okay, live session. The 9th class live will be on Thursday. It will be on every Thursday 5 p.m. We will discuss these questions in those lives. So make sure you join that live, subscribe the channel for that. Okay, and you go through these questions and you let me know what you think about the answers of these questions. Okay, some of the proud moments as we the people of India is your BRC Mumbai. It runs neutron scattering with reactions like dhruva, that is your atom, and it results in superconductors, battery electrodes, drug molecules. It helps in all of that. What are the scientists we studied? We studied about Thomson. He told that electron exists. Rutherford, he told that protons exist, nucleus exists. Bohr told that there are specific energy levels. Chadwick told us that there is something exists, that is neutron, and they all won Nobel Prizes for that. And we have H.J. Baba, on whom this BARC Baba Atomic Center was being made. He was the first to lead this nuclear program, these nuclear forces between electron, proton and neutron on the nuclear level, smaller level. We study these with big accelerators, big microscopes, and father of India's nuclear program, founded TIFR and BARC. It is one of the best institutes of India to do research on these kind of topics. If you see, there are like 4 buildings, big accelerators in those buildings. There are 2 rooms, big microscopes in those buildings. So this is something worth going into, I feel like. Okay, and if you also love the research, you can go into those as well. So for that, never stop asking questions. Let's do some questions. Okay, now, gold foil experiment, choose the correct option and explain each. It clearly showed neutrons exist in the nucleus. Gold foil, Rutherford. No ma'am, neutrons was told by Chadwick. So, this is wrong. It disproved the plum pudding model and led to the idea of nucleus. That is true. That all the mass is concentrated at the center. That was done by gold foil experiment by Rutherford. Large deflection of a few particles, mass and positive charge packed in a tiny center. That is true. The deflection showed how electrons move around nucleus. That is not. That is shown by Bohr. That is actually the limitation of gold foil or Rutherford. Right? According to Bohr's model, which statement are correct? Electrons lose energy in a fixed orbit and slowly fall into the nucleus. No, that was Rutherford. Bohr said no. Right? Electrons can exist anywhere around the nucleus with no fixed energy. That's also wrong. Electrons revolve in orbits of fixed energy without losing electron energy. That is true. Electrons can be found between energy levels. No, they can only found in the energy shells, in the stationary energy levels. Okay. Oh, this is good. Isotope, isobar, great example. For species X, Y, Z, explain the relation between Y and Z and X. Okay, let's do this. It's very interesting. Now see, we have isotopes and isobars. Let's just write what are those. Isotopes, bacha, are made up of different elements. I have wanted you to remember from this. And they have different, they are made up of same element. They are made up of same elements, carbon, 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 hydrogen, 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 and they have same atomic number, hence different mass number, right? On the other hand, isobars are different elements, hence means different atomic number and same mass number. Understood? Very clear? Whenever you get a question of isotope and isobar, just write these two lines. Okay? Now, protons and neutrons. We have an element X. Let's write its symbol. Every time you see, you have to write the symbols X, Y, and Z. Okay. Next, beta, we have number of protons. Number of proton is your atomic number, right? It is your atomic number. So 18 I will write here, right? And neutron, mass number is what? Proton plus neutron, right? And this is what? 18 plus 19. That is how much? That is your 27. 27. Understood? 37. Sorry. It is 37. Done. Similarly, you do for Y. Y, we have atomic number, that is 17, and we have 17 plus 18. How much is that? That is 35, right? Then beta, we have 17 plus 20. 17 is atomic number, and 20 plus 17, that is your 37. Now just see, we have to see a relationship between Y and Z. Y and Z, same atomic number, different mass number. Same atomic number, different mass number. So Y, so this was Y and Z. Y and Z beta, Y and Z are your what? These are your, where should I write? See, Y and Z are your what? Isotopes. They have same atomic number, different mass number. So they are isotopes. Now, X and Z, different atomic number, same mass number. Different atomic number, same mass number. Those are your isobars. So X and Z beta are your isobars. Understood? Understood? Easy? How easy it got if you write just this one statement. What did you remember? You just remember that isotopes are same element, isobars are different element. That's the only thing you have to remember. Okay? Then, next beta we have, what did Rutherford conclude about the position and nature of the atoms? Positive part from the few alpha particles that bounced back or were deflected at large angles. He concluded that at the center of the atom there is a heavily positive charge and it is concentrated in a tiny place, that is at the center. It consists of most of the mass of the atom and it is of positively charged. Then arrange the correct chronological order. Okay, so first order given by Bohr, no. Thomson, no. Rutherford, Dalton. Dalton gave the first order, so Dalton is first. Then came Thomson, then came Rutherford, then came Bohr. So 1, 3, 2, 4 will be your correct order. Next beta, we have assertion reason question. The discovery of subatomic particles helped understand the atomic structure. Okay, yes, it did. Subatomic particles are what? Electrons, protons, neutrons. So they helped understand atomic structure, obviously. The number of electrons equals the number of protons. Number of electrons equals the number of protons. Okay, but both of these are true. But this reason is actually not the exact explanation of assertion, right? So both are true and both true are does not explain A. Second will be your correct answer. Okay. Then beta we have magnesium. Again, one more good thing. Magnesium is vital for muscle contraction. For a magnesium atom with mass 24, we have a magnesium atom whose mass is what beta? 24, and atomic number is 12. Number of protons. How much number of protons are there? Equal to atomic number, that is simple, 12. Number of electrons equal to atomic number, that is 12. What are neutrons? So mass number is 24 mass number, this is your magnesium atom, we have mass number as 24. Now beta, you can take out a formula out of it as well. Okay, so we have mass number equals to proton plus neutron, right? This proton is already equal to atomic number, right, plus neutron. This is your mass number. So formula for number of neutrons is equal to mass number minus atomic number. This is one of the formulas that if you remember, it will be easy, otherwise you'll have to think all through it. Okay, so this is A, this is Z. Number of neutrons will be what? A minus Z, that is 24 minus 12, that is 12. So this is your also 12. Okay, and illustrate the arrangement of electrons in a magnesium atom. So we have K shell, L shell. Let's fill up the electrons for magnesium. Now magnesium have 12 electrons, right? It has 12 electrons. So how will you fill it in the shells? This is your positive charge. Okay, this is your positive, oops, this bacha is your positive charge. Okay, now let's fill up the electrons. So in the first shell I will have 2 electrons, in the second shell I will have 8. 1 2 3 4 5 6 7 8. So 2 plus 8 10. 2 more are still left, so I will have to make one more shell. I will have to make one more shell, and that is your KLM and shell. This is KLM shell, and here you will have 2 more electrons. Done. And what will be the valency? 2 plus, because it can lose 2 electrons, because this is an octet. Done. Understood? Then beta, we are finally done. One more we have an atom. X80 has 31 electrons. How many neutrons are in its nucleus? Okay, this is your homework. Okay, answer in the write down answers in the comments below. Okay, that is your homework. This is your homework. I will see whoever wrote the answers. We already did this, right? X has 80, electrons are 31. So this is your hint as well. Okay, beta. Now we have completed almost all of it. Okay, beta. Next. Now, yes. Okay, now we have finally completed the chapter. For more questions, do come into the live sessions. Okay, every Thursday 5 p.m. for 9th class, every Wednesday 5 p.m. for your 10th class. Okay, that is it for this chapter. It was a little cinematic, I hope. In your mind, you have to think of it as a cinema. Dalton, Thomson, Rutherford, Bohr. Okay, and that's how you will be able to learn it. And we learned some few more concepts. It's a very, very important chapter. A little bit difficult, I can get it. There is lots of things to comprehend, but a very interesting chapter, very easy chapter, the way your Aditi Ma'am told you. Okay, now if you are still in this video, comment down whatever doubt you have, or comment down that you like this session or not. I will meet you in the next one. Tata, bye bye.